All right, exponential growth and decay. This is 4. A solution to a differential equation is a function that its own derivative, which what we've been talking about is if we have a differential equation, we get a solution by taking the antiderivative. If k is a constant, this is a differential equation. So in other words, I'm just saying a constant times some value. And so this rate of change here, y then, is proportional. So we could call this a constant of proportionality is whatever this value of k is. And so this differential equation, we're going to actually see that there's a for it, and that's the solution. So this is kind of when we first did differential equations, we would say, check that this is a solution to this differential equation. Remember, what you do is the first thing I would do is take the derivative of y. So I just plug that in here. If I take the derivative, remember this is that e to the kt thing, so you need to bring the k down. That's just a constant. And so now you can see that this piece right here is, and so I just simply plug in the y. My left side equals my right side. This is the kind of things you would see on OMG, we got a test on Tuesday, right?
What test?
Oh, now I got your attention. Yes. So the test, I mean, I'm going to certainly pull problems out of Wiley, like problems like Wiley, in other words, but you certainly need to be able to do all of those problems. I will try to get something together to send you and say you should be able to do problems like this. This would be a good example. Yeah, Rachel?
So the CEKT, would that always be there? Like it would be given, right? You don't have to take it.
Right. So in other words, this is saying just some constant. You're going to see a bunch of examples of these. This constant times this exponential equation. But yes, this would be given. Sometimes, though, you have to find these values. And that's what we're going to do with all the examples today. Yes? Oh, I can't go back. You know that. It's right here, though.
Okay. Why does y only equal e to the kt, not like the full thing?
As soon as I saw that, I saw it in bold and red. Yeah, it's the C as well.
Okay.
Yes.
So it's everything. It's all
Yes.
Okay.
I thought you hated C.
But there's a K in there, and that made me nervous with a C and a K. And
You can say A not.
I'm still going. All right, so notice here, these are my values of K. This is just an exponential. Who cares about this constant? The constant's just bringing it, bringing the function up or down. In this case, spreading it out. But what I'm looking at is if I look at various values of my exponential, if I have positive values, certainly my function's going to go up. If I have negative values, my function's going to go down. And now these are all dependent as well on my constant function. So if I have a positive value in my constant and my k is positive, that would be an exponential function that's increasing. Again, you're going to see a whole bunch of examples of these. And so you need to know basically this k here if it's positive or negative. The easiest way is things like population. They're growing, so that would be positive. Okay, that's this value right here, remember, is your constant of proportionality. So it changes with whatever your population is. If it's a drug leaving the body, then of course that would be negative, okay, because your constant's going to be leaving. All right, so find the general solutions to these following differential equations, a Wiley thing. If you notice, every one of these, I just want to let you know the corner store has free Powerade right now. How do I get these texts? All right, so anyway, if you look at each one of these are a constant times a variable. Okay, that's all they are. So if I have a constant times my dependent variable, notice my dependent variable is the variable up top, then each one of these I could rewrite with the general solution. So this is kind of what you were asking, Rachel. Will it always be like this? Yeah, if you have this form where you have a constant times your variable, then I can rewrite this, that this is my k, that was the ky, and I can write that up here. Notice here, though, that my variables are changing because this is my variable of integration. Yes, sir?
On Wiley, when I was trying to do this, they were asking, like, they said a different variable for C. Like they said for B, like P not E to the negative 0.3 T.
I will be doing that example. Yes. Actually a good one. All right, and so in other words, this is a general solution where C's an initial, and that's what I started to call you Ben, but if you were Ben, you would be number 6. We just keep moving you down. All right, and so in other words, this would be an initial value. So at a beginning of time, what's the initial population? P sub 0, like Justin was saying. Or you might have, I was thinking of Ben again, of the caffeine, you know, the initial amount. And so examples of this, of course, would be population growth and decay of a drug in the body. So if I have population P for a region with no immigration or immigration, nobody's coming in and nobody's going out. Sounds like a... So the rate at which the population is growing is often proportion to the size of the population. Meaning, in other words, the larger the population, you got more people having babies, so it's going to grow faster. But population things that work with these exponential functions. So if the population has a continuous growth rate of 2% per unit of time, whatever years we're looking at, then we know that the rate of growth of the population is 2% times the current population. That is an actual constant of proportionality times a variable, so you know that this would be exponential. So I could write my differential equation simply by 2%, 0.02, times whatever the population is at that time. Some of the beginning of these problems, they ask you just to write the differential equation. And so if I take my differential equation, if I lose my voice, then we'll just have the quiz now. All right, and so if I find this general solution, again, this is what we just saw, that constant of proportionality times my variable of interest. I can rewrite this. This is, I didn't use a C, I used P sub 0 because it's the population, the initial population. This is my E to the KT. This is positive because the population is growing. And so typically, and this goes back to what Rachel was asking, typically you would be given this and you would have to turn it into this. And then you're going to use this like you have, what's your initial population? You plug values in at a certain time. Now what would the updated population be?
How do you do P naught in Wiley?
Is there a box to do subscripts? Subscripts, yeah.
Oh,
For the previous slide where it was saying POE.
P sub 0.
Yeah. That one. So you get that from taking the ln and the antiderivative of the first.
Yes, and you're going to see us go through. Yeah, very good. That when we have to solve it, yes. All right, so here's another one. We have a constant of proportionality, the rate at which a drug leaves a patient's body, maybe I have a cough drop, is proportional to the amount present. If Q is the quantity of drug present at time t, so in other words, this is my constant of proportionality times how much of the drug is present. It's negative because hopefully, unless you're a druggie, I guess the drug's eventually going to leave your body, okay? So here we can move from, what you were asking, we can move from this to our differential equation. But the biggest point here is this K value, this constant of proportionality of recognizing when it's positive, when it's negative. I remember Justin mentioning last time you recognized, oh, that's a decay function. And that's what this is, okay? When you have negative, something's decaying or leaving in the body. So how could I write this, okay? And all of these are going to be the same. If you have a constant times this variable of interest, these are all going to be that same function. Man, I feel sorry for anybody listening to this recording. All right, and so in other words, and here it doesn't matter. When I typed this in, I thought students are going to wonder, why did you do Q of t when you've just been doing Q? I could write Q, but this is a function of time. So this is my initial amount in the body, and then this piece right here is saying how fast is it decaying. Again, if you kind of look at this exponential, if it's decaying, it's going down. So this is really the important part. This is just the initial amount that's in your body. All right, find the solution to the differential equation. Again, a Wiley example. The only difference here is they give you the initial condition. So that's my constant of proportionality. Again, just recognizing a constant times my variable of interest this will always be the solution. Always, 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 always. Okay, so now I see what I plug it in. I use this information. It says that my initial, it doesn't say what this is, but let's say it's population. My initial value at time equals 0 is 12. So then I just take this, solve it for C to find is. This, of course, is going to be e to the 0, which is 1. So I just get C equals 12. And then that becomes my value for C. So this is very important, that when we started with this, we said, well, we had some P equals P sub 0 e to the KT. That's everything when we first started this. Well, now here we're saying, I want to know how this population is changing, and this population's increasing. I'm saying population, it doesn't say that, but let's go with it. This is increasing because that's positive. This says the initial value, okay, so in other words, that's this piece right here. It kind of goes together why they write it as P sub 0, because that's the very beginning. Then P sub 1 could be after the first year. P sub 2 could be after the second year, and so on. Well, how would you get those values? You'd plug in at the end of the first year, second year, third year, and so on. You'd plug in values for T. All right, the amount of ozone Q in the atmosphere is decreasing at a rate, right there I see decreasing, so I know something's going to be negative, at a rate proportional to the amount of the ozone. If T is measured in years, the constant of proportionality, they give it to me. Okay, so sometimes this will be given to you, sometimes you have to solve for it, what Rachel was saying, how you go through the steps and do logarithms, and we're gonna do that. But this was given, but again, it's recognizing, I mean, this could be a test question, why would this be negative? Because it's decreasing, an easy test question. Write a differential equation for Q as a function of T. Go, what is it?
Negative 0.0025 times Q.
Yeah, so a differential equation, okay, this is different than that CE to the KT. The CE to the KT is the solution, the original function. I need water. Lay your heads down and take naps till I get back.
Wait, can I?
No, you can't. Whatever it is, you keep. That would have been much better if that was beer coming out of that. Oh, was I recording that? Yeah. All right, so remembering that this is my differential equation. When we were working backwards, that whole C e to the KT is my original function. You could think of this is the derivative, that was the antiderivative, same thing. Okay, we're just not having to figure out what the antiderivative is, I'm giving it to you. All right, so give the general solution for the differential equation you see to represent any arbitrary constant.
Q naught e to the negative 0.0025 times Q.
Very good. I use C, I'm sorry. I probably would have used Q naught, okay, the initial value, but they did say to use C. And so remember, this is my K, so this format's always going to look the same. You're going to have some constant, E raised to your constant of proportionality, which they give to you, and then times T. So as you can see, all these functions is something increasing or decreasing over time. If this rate continues, approximately what percent of the ozone in the atmosphere now will decay the next 22 years? What do you do with 22? In other words, as he's saying, you would just multiply it by this value. They show in the book to stick it in here because you don't really care about this constant, okay? That can be ignored, but you get this value. Because this is a rate, I probably would have went and stuck it into the original equation, okay, which would have been this value times the 22. And so if I write that as a percent, approximately 94.6% of the current ozone will still be here in 22 years. I guess that's good for you guys. I'll probably be dead by then. And so this would be the amount that would decay. I could be. You're watching too much Story. I'll probably be pickled, huh? All right, example 3. The rate at which a drug leaves the bloodstream and passes into the urine is proportional. That's the key word in all of these, is that constant of proportionality to the quantity of the drug that's in the blood at that time. If an initial dose, Q sub 0, there you go, Justin. I keep wanting to call you Ben, is injected directly into the blood, 20% is left in the blood after 3 hours. Write a differential equation, go. 0.2?
0.2.
Q times Q. So I'm going to end up with, after I get my differential equation, I'm looking at this quantity of drug in the blood after T hours. In other words, I'm skipping that step, what you guys said, which is fine, the 0.2, this piece right here. Well, this says this is the quantity of the drug in the blood after, in this case, 3 hours. So that's my time. I just flip these values around. So basically what I'm trying to solve for is, in this case, this K, the constant of proportionality. So if I do that, probably the first thing you see is the rows wipe out. Okay, so I just divided both sides by those to cancel them. And then now where we need to solve that using logarithms. So I'm just trying to find, when you're solving for K, the constant of proportionality, you're wanting a general equation for any time. And so I'm just using this time, 3 hours, to actually get this value. So continuing on, take logarithms. Be sure on your next test you have some kind of calculator that will do logarithms. And so take log sides. This, of course, comes down. That cancels out. And so I take logarithm of this, and now I would divide -3. Okay, just the algebra of solving this. You have no problem with those steps. And then I get my value of K. So that's my constant of proportionality. So I can go back, which I'm going to do, and plug that into my equation. So those steps, you're certainly going to have to do something like that on the test. Okay, because you're going to see here in a minute on the slides, I just skip all those steps and say you basically go back through all these same steps. So this is my constant of proportionality. Now I have, and that's why this is called the general solution. This is for any time. And it's actually for any value, the initial quantity of drug in the body. So how much of the drug is in the patient's body after 6 hours if the patient is given 109 milligrams initially? Well, of course, this is my initial amount, and then that being time. And the reason this is like a huge decimal, this is an exact Wiley one, and it says round to the nearest integer. So be sure you're reading that if you get some of these wrong, it's just from rounding. So this would be how much it would be in the patient's body after 6 hours. All right, half-life. Sometimes physicians convey information about the relative decay rate with a half-life. In other words, how a quantity can decrease by a half-life, meaning in half the time. That's all it means. And so if I'm talking time, I would say, well, in a year, half of it. And so the half-life of this drug is about 3 days. If 50 milligrams dose is given, when is the quantity remaining at 6.25? This is a half-life, meaning you're half in it. So the half-life is about 3 days. If we start with 50 milligrams, how many days till it reaches that value? How many? No, I didn't hear you.
12.
I hear 9. Who said 9? You said 12? I'm like, I don't even see a 12 up there. Apparently the answer is not 12 because I didn't see it there. Yeah, so in other words, after 3 days, the quantity is halved. So 50, half would be 25. After 3 more days, it's halved again. So half of 25, 12.5. After 3 more days, it's halved again. And so 369 would give you 9 days. So all this is doing is the half-life is saying it's taking this and halving it, halving it, halving it. When does it reach that value? All right, this acid is a drug used to control epilepsy. Its half-life in the human body is about 15 hours. Use the half-life to find the constant K in the differential equation, and then at what time will 10% remain. So let's do the first part. The first part, I'm basically, the half-life says I'm taking half of the quantity present, and my time is this 15 hours. So I simply, when I want to find this value of K, I plug in everything I know. So this is my quantity present. When is it going to reach half? Another example I did, the one before, is a lot of times you will see this written as multiply by 0.5. Of course, it's the same thing. So sometimes I might write it like this, or 0.5. Again, looking here, this is just like the one before. I would solve for K, and this is where I get to the point where I'm not going to go, when is our test? I'm not going to go through all of the steps to say, I'm going to tell you what the answer is. So this would be a very good example that you could go through all those steps. Once again, I would have divided both sides by Q sub 0. I go through all the steps until you get where you can solve for K, because you certainly need to be able to do that. Jace, no problem, right? Miss, I'm looking at you, Corey.
I don't know, I'll figure it out in test.
That's what I figure. At what time will 10% of the dose remain? Well, I want to know 10% of the dose, of the amount that's in there. And so I would solve this now for T. You can do that as well, right? Divide both sides by Q sub 0. You're still going to do logs. You're still solving for the variable. So I plugged in, this was my K that I found on the previous slides. And now I'm trying to see when it hits this 10%. And so I'm getting the time, and it's about 50 hours later. These would be really, really, really good test questions. Wait.
No, I said wink, wink.
Oh, wink, wink, hint, hint, wink, wink, nudge, nudge.
I don't know what you're trying to do, but okay.
Oh, what a shame. That's the last slide, meaning we have time for a quiz.
Would you say make more stories like this?
Pretty sure, Cindy.
What about what?
What do you think of my project is like this? Like,
Why is it 12 point, why is it 12?
Maybe.
I needed to know.
Remember, I'm not helping you. Why did I? Oh, yeah.
we not growing
That's my other class.
I needed to know
Cindy.